We've talked about the behavior of electrons and atoms. We talked about all those very confusing orbitals and subshells and quantum numbers and all of that stuff. The electrons in atoms exist within orbitals. Orbitals, remember, are a region of space defined by a wave function, and it's a region of probability. The electron is most likely to be found within that volume, but it does not predict exactly where it is. It is not a fixed orbit. So to describe the orbitals in an atom that are actually occupied, we use what's called an electron configuration. And the one for hydrogen is very simple. Hydrogen only has one electron. And so the orbital is listed here, 1s. So this is the s orbital in the first principal energy level. So the quantum number is 1, and m sub l, principal quantum number, is 1. M sub l would be 0, because that's the s orbital. The superscript here tells us how many electrons are in that orbital, in the subshell. So here there's just 1. Schrodinger's equation, which we just looked at a very simplified version of, you can do calculations and show that hydrogen's 1 electron occupies the lowest energy orbital in the atom. For multi-electron atoms, everything but hydrogen, the equation can't actually be solved. It can be approximated, and the approximate solutions show that the orbitals are like those in hydrogen. And so that's what we're going on. The reason it gets complicated is you've got interactions between electrons within the same atom, and that makes the math even more complicated. So we need to talk about 2 additional concepts that are going to affect all the other atoms besides hydrogen. And these are electron spin and energy splitting of those sublevels. So electron configurations are things like 1s2, 2s1, those sorts of things. Orbital diagrams, as the name implies, it's a diagram of the orbital. Here we're going to use little boxes. Each box represents 1 orbital, and the electrons are indicated as arrows. So it's a half arrow, and the direction that the arrow is pointing in tells us the spin. So this would have a positive spin, and if we drew it upside down, it would have a negative spin. Remember, spin is that m sub s, the fourth quantum number, and it can be either plus 1/2 or minus 1/2. And we've just decided that up is positive. So if you looked at a group of hydrogen atoms, we'd see that about half of them have that 1 electron with spin up and about half with spin down. The Pauli Exclusion principle says that no 2 electrons in an atom can have the same 4 quantum numbers. Okay, it's sort of like you can't have 2 people with the same social security number, right? You can't have 2 people with the same Fresno City College student ID number, right? It's a unique identifying set of numbers. So if we have 2 electrons that are in the same orbital, they're going to have 3 identical quantum numbers. The principal quantum number, I always forget these names, L and M sub L, those are all going to be the same. And so the 4th quantum number has to be different. That means that one of the electrons would be plus 1/2, and the other would be minus 1/2, in that m sub s. So what we get from this, and this is what you really need to remember, is each orbital can have a maximum of 2 electrons, and they have to have opposing spins. So we're going to go through some stuff, and it's probably going to sound like Charlie Brown's teacher, and then hopefully I'm going to bring you back to the quantum hotel, and hopefully things will get a little clearer there. When we know the number of orbitals in a sublevel, we can figure out the maximum number of electrons that could be in that sublevel. So the S sublevel has one orbital, and we identified that by looking at the different quantum numbers. So it can hold 2 electrons. The P sublevel has 3 different orbitals. Do you remember the shapes of those? The S was spherical, and the P looked kind of like a dumbbell or 2 balloons tied together, and they had different orientations. They were at right angles to each other. And we don't even want to talk about the shapes of D and F. But it goes 1, 3, 5, 7, 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. Each orbital can hold 2 electrons. Remember in the quantum hotel, each orbital, the orbitals were beds. How many people typically sleep in a bed? 1 or 2, right? Maximum of 2. So the number of electrons is twice the number of orbitals. So let's look at the quantum numbers for the electrons in helium. So there are 2 electrons, and they're going to be in the lowest energy orbitals that they can be in. So their principal quantum number is 1 for each, and in that first level, the only option for L is 0. So they're in the S orbital, so that's where we get this 1s. I believe this was the angular momentum. The options here are only 0, because m sub L can go between minus L and plus L, so it's still just 0. There's only one orientation for an S orbital. And if you think about it, it makes sense, right? It's a sphere. It's symmetrical in all dimensions, and so you can't really talk about an orientation. You look at the ball, it's like, well, which side of the ball is up? Well, a ball doesn't have a side, right? So it can't be up or down. Both the same. So here, the 3 quantum numbers identical. Something has to be different somewhere, so it's got to be this last one. So one has a positive spin, one has a negative spin. We don't see that in the electron configuration. Electron configuration ignores spin, doesn't come in there at all. In the orbital diagram, though, we're going to show 1 arrow up and 1 arrow down. And in my quantum hotel, remember, so here's the bed, the pillow. That's kind of a skinny bed, but, you know, whatever. It's a discount hotel. So one person, come on, don't freak out on me. One person sleeps like this, and the other person sleeps upside down. So this is the spin up, and that's the spin down. So when I see these little boxes, there's 2 people sleeping in the bed. Yeah. Anyway, any questions about that? It's weird. So m sub s, one of these is positive 1/2, one's negative 1/2.
So each row represents 1 electron?
Yes, so this would be for the 1 electron, and this would be for the other electron. So they're in the same orbital because 3 quantum numbers define an orbital. 2 quantum numbers define a subshell, 1 or a sublevel, 1 defines the level or the shell. Oops. So the sublevels in each principal energy level all have the same energy. The orbital energy depends only on n. And so the word we use for this is degenerate, things with the same energy. So all of the orbitals in a given principal energy level for hydrogen have the same energy. It's only true for hydrogen. When we get to more electrons, everybody else, the energies of those sublevels are split. They're not the same. They are not degenerate. This is caused by charge interaction between electrons, by shielding, and by penetration. And so in general, the lower the value of L within a given principal level, the lower the energy of the orbital. So S, P, D, F in order of increasing energy. So if we were looking at perhaps the 4th energy level, So n equals 4. 4s is going to have less energy than 4p. 4d is going to be more energy, and 4f will be the orbitals with the highest energy. In the quantum hotel, this amounts to different rooms costing different amounts of money. And so the F rooms are going to be more expensive on the same floor than the S room. And if you want some rationale behind that, the S room might be by the elevator or the ice machine, and so it's kind of noisy. And the F room is down at the end of the hall, and it's quieter, just more desirable. So to talk about, we have to talk about these three different effects, the charge interactions and penetration and shielding. So Coulombs Law describes the relationship between charged particles. There are different, we sometimes see it as force is equal to, this is the energy. So the energy of, potential energy of two charged particles depends on their charges, Q1 and Q2, and it also depends on how far apart they are. And I think we've all experienced a phenomenon like this with magnetic fields. The magnet, how far it is away from the refrigerator, makes a difference in how well it sticks, right? So you've got a regular old magnet and you stick a piece of paper up there, it sticks just fine. So then you put 2 pieces of paper, we're fine. 3 pieces, maybe it's getting a little shaky. Eventually, just by adding pieces of paper, you've got that magnet far enough away from the refrigerator door that it's not going to stick anymore. The potential energy that's attracting the magnet to the refrigerator depends on not only the strength of the magnet, but also on the distance between the magnet. Okay? When you hold a magnet, 2 inches from the fridge, it has no attraction at all. The same is true for opposite charges within the atom. So the nucleus has a positive charge, the electrons have a negative charge. The electrons are attracted to the nucleus, and how attracted they are depends on how far away they are. It also depends on their charges. So if the electron charge doesn't change, electrons are always a -1 charge, but the charge on the nucleus can change depending on how many protons are in there when you compare different atoms. If these charges are the same, meaning they're both positive or both negative, then delta E is positive and those charges repel each other. If they're opposite in charge, they attract. So potential energy is going to increase as the particles get closer together. The amount of repulsion gets stronger, or the amount of attraction gets stronger. Does that make sense? You do not need to know this 1/4 pi epsilon naught. That's just a constant. So what is good to remember is that the potential energy is proportional to the charges multiplied by each other divided by the distance between them. So this is a good thing to just kind of keep in your head. So each electron in most atoms experiences an attraction from the nucleus and repulsion by other electrons. They're like, I'm really attracted to this nucleus, but it'll get away from me, right? That electron over there, I don't know about this. So there's this conflicting attraction and repulsion. So the repulsions cause the electron to have a net reduced attraction to the nucleus. We say that it is shielded from the nucleus. Do I have a picture? Don't have a picture. I'll draw a picture. So let's do lithium. Let's talk about lithium. So in lithium's nucleus, how many protons are there? 3. So it's got a 3+ charge on the nucleus. And then we've got 2 electrons. I'm drawing the Bohr model just because it's so much, I can't draw the quantum mechanical model. There are 2 electrons in the first energy level, so n equals 1. And then in the second energy level, there is 1 electron. It's a total of 3 electrons. So this electron, this has a -1 charge. These are negative as well. This electron is looking at that nucleus and thinking, I'm really attracted to that +3 charge. But then closer into the nucleus than this one is are these 2 electrons that are kind of zinging around in here in their little wave function orbital business. And those kind of cancel out or subtract from the attraction of this. Does that make sense? So these are closer in, and so when this electron looks over here to see the nucleus and be attracted to it, these electrons sort of shield it from the nucleus. And so the effective charge, what's called the effective nuclear charge, so the effective nuclear charge for that guy is going to be the charge on the nucleus, which is +3, and subtracting the number of electrons in between. And so there's 2 of them. And so it's going to see an effective nuclear charge of +1. These electrons have nothing shielding them from the attraction of the nucleus, and so they see a +3 charge. But this guy out here, these electrons shield it. Does that make sense? So that's shielding. And then penetration has to do with the distance. So the closer an electron is to the nucleus, the more attraction it experiences, because E is proportional to Q1, Q2 over R. If R gets bigger, this is a smaller number and the attraction goes down. I'm sorry. If this is a smaller, I said that exactly backwards. If this is a, I don't know, now I don't even remember what I said. I'm going to start again. I don't know. If this is a large number, this term is smaller and the force of attraction is smaller. If this is a small number, if the electron is close to the nucleus, then it's going to be more attracted. So the closer the electron is to the nucleus, the more attraction it experiences. For those outer electrons, some of those orbitals sort of penetrate, they get into the cloud of the electrons that are close to the nucleus, so they penetrate in, and we get more attraction than we would necessarily expect for them. So the degree of penetration is related to the orbital's radial distribution function. I know you're happy to hear about that again. Oh, here's the picture I was looking for. So, shielding. Oh, look, it's lithium. +3, and then there's these 2 electrons. This third electron is going to experience a net charge of about +1 because these 2 electrons shield it from the charge on the nucleus. Penetration means that if this electron can get in here where these electrons are as well, if it can penetrate this inner electron cloud, then it's going to experience a full +3 charge, and it'll be more attracted. So not only is it getting a higher attraction because of the charges, it's also getting a higher attraction because it's closer. That makes sense? Think about magnets. So some orbitals penetrate more deeply into the inner orbitals than others do. And so here's that radial distribution function. So what we're seeing here, this is the 1s orbital. Those are the 2 electrons in lithium that are shielding the third one. If we look at the radial distribution for the 2p and the 2s orbitals, we see that the 2s orbital has this node here, but it's got this bump right there. And so an electron in the 2s orbital might be found in here, which is within the 1s orbital. And so then it's going to not experience the shielding, and it's going to experience more charge also, more attraction also due to being closer. So the 2s orbital can penetrate into the 1s orbital. The 2p orbital does penetrate some, but not as effectively. So with this interaction between electrons, we find that the 2s orbital is lower in energy than the 2p orbital. And that's not the case with hydrogen because there's no shielding effects. But the 2p and the 2s are not the same in energy. Yes?
Can you say the difference between shielding and penetrating again?
Yeah, difference between shielding and penetration. So shielding is this effect where electrons that are in lower shells within the atom. So these would be n equals 1 electrons, and this is n equals 2. These guys are closer to the nucleus, and so they're going to shield this from the charge of the nucleus. Okay, this is kind of a weird. So here's the electrons. I think of those as masculine, and here's the feminine nucleus, and she's really hot, +3. Well, how does she keep all the guys from going crazy over her all the time? She puts on ugly clothes, right? So she's got clothes on that covers some of her beauty and attractiveness. This is I don't plan these things, they just come out. Okay, so these are like clothes. She's got this big winter parka on or something. Well, that reduces the attraction that this guy feels for her, right? It's like, oh yeah, I think you're cute, but I don't know, hard to tell with the parka on. You get inside the parka, you get inside closer where you can really see her, and now there's more attraction. I don't know, does that help at all? It's a little, not with the whole word penetration, you just go somewhere very bad with that. Yes?
So why are the experiences different for carrying its full 3+ charge and then the...
Okay, so why is this one experiencing something different than that one? Because it's able to get in here. That's the penetration. And the y is in this graph.
But wouldn't it be 0 instead of 3+? Because all 3 are...
That's a good question. So why isn't this a 0 charge instead of 3+? Because see how close this guy is? Are these guys getting in its way at all? No. It's when we have these in a lower energy level than this one, then they will shield. Because this one then is pretty much outside. It's zipping around out here. The reason that there's penetration at all is because these orbitals actually overlap with each other. Okay, and the 2s orbital overlaps and gets in closer to the nucleus than the 2p orbital does. The 2p orbital also overlaps, but the s does it more. There's more penetration in the 2s orbital, and so there's more attraction of the electron for the nucleus. In the 2p level, there's less attraction, and so that's a higher energy state. High potential energy means that something's more likely to crash to the ground, right? You lift a piano 1 inch off the ground, it has potential energy. You hang it outside a second-story window, it has more potential energy, right? So you can think of the nucleus as being the Earth and the electron being attracted to it. Potential energy, the farther away it is, the higher the potential energy. No, that's not working. The higher the energy of the orbital. I really need a back button and just rewind. I should edit this later, but I'm not going to. We're going to go on unless there's any other questions, because I'm just making it worse at this point. So what we see is as we get higher principal energy levels, higher quantum number n, then the effects of penetration become more and more important. And they become so important that the 4s orbital is actually lower in energy than the 3d orbitals. And so they begin to overlap. And to make things even worse, the relative energy ordering can actually vary among different elements. Other than hydrogen, we're going to ignore that. Okay, so this is what it looks like. This is the effect of the interactions, of the shielding and the penetration. So the 1s orbital is the lowest in energy, and the 2s orbital is next. The reason that 2p is higher in energy is that 2s is better at penetrating and getting close to the nucleus. So in hydrogen, these are all at the same level. But in all other elements, the 2s is lower than the 2p. Then we go up to the next quantum number, n equals 3, and we expect that this is higher in energy than the 2p, and it is. And then next, on that third level is 3p, and those are higher in energy. And this is where things start to get mixed up. We would expect that, bless you, 3d would be next. But the 4s penetrates better than the 3d orbitals, and so it's lower in energy than 3d. And so it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and it just starts to sound like a bunch of numbers and letters. I'm not wanting you to remember the order right now. I'm trying to help you understand what's happening here. Because what we're going to find out is this order is all hiding on the periodic table. The periodic table is a crib sheet for this. Okay? The Aufbau principle is that electrons are going to occupy orbitals to minimize the energy of the atom. So they're going to fill up the lower energy orbitals first. In the quantum hotel, this means the electrons are cheap. They are at a discount hotel, after all, discount resort. And so they're going to take the cheap rooms first. And that's what the electrons do. They're going to fill the lower energy orbitals. Orbitals within the same sublevel have the same energy. So here's the 2p sublevel. There's 3 orbitals there. Those are degenerate. They're all the same energy. So the electrons are going to come in, and like if we were just sticking electrons in here, we'd put 1 there and then 2, and then here, and they would fill up like this. And then they'll go up to here, and then they'll go over here, and we're going to go through that a little bit more. So this is the filling order. Again, we're going to see how that is hiding on the periodic table. The orbitals can hold no more than 2 electrons each, and the spins have to be opposite. That's the Pauli exclusion principle. Hund's rule says that when you're filling degenerate orbitals, fill them singly first with parallel spins. Okay, so the quantum hotel. Discount resort for electrons in Mrs. K's chemistry land. So the first floor in this hotel has 1 room. It's the S room. Second floor has 2 rooms, S and P. Third floor has 3 rooms, S, P, and D. You get the idea. Each S room has 1 bed. P rooms have 3 beds. D rooms have 5 beds. F rooms have 7 beds. This is a very strange hotel. The rules are only 2 people per bed. They have to have opposite spins. I've interpreted this different ways, but I like the sleeping upside down one the best. And so if you're confused, this is your key here. A floor is a principal shell or principal level. A room is a subshell or sublevel. A bed is an orbital. A person is an electron, and money is energy. Okay, so this same diagram is my hotel. Let me put some walls on it. And the electrons come to stay at the hotel. Pick an element. Potassium. Yeah, that's good. So potassium has 19 electrons. So the potassium bus shows up, and we've got 19 electrons that need to stay in the hotel. So this is how we're going to put them in. So the first one comes in here because the 1s room is the cheapest. So the first electron in, I'm going to stay in this room. The second electron, remember, energy or money is the biggest motivating factor. The second electron is also going to stay there. It's like, I'm not sleeping right side up next to you because that's just gross. So the third electron comes in. He's going to take the 2s room. And the fourth one comes in, and he also takes the 2s room. The next one comes in. He's like, I'll take that first bed in the 2p room. Now the next electron comes in. There's still room in the 2p room, and so he's going to come in here. Now think about it. You're going to sleep upside down in the bed with this guy, or you're going to take your own bed? You're going to take your own bed, right? And you're going to sleep right side up. Okay, so Hund's rule, when you have two orbitals, two beds, the same energy, they're going to fill them separately first with parallel spins. The next electron is also going to take his own bed. Okay? The next one that comes in, what's he's going to do? What is he going to do? He's going to sleep upside down with one of these guys. And then here, and then here. So the next one comes in here. 4s. And then another one in here. Because he would rather share with this one and save the money than pay more and go to the next room. But then we get to this room with the 3 beds again, and they're going to fill like this. Each taking their own bed, sleeping right side up. They'll make the guy coming in next be upside down. And then we've got one more, and he's going to be in the 4s. So if we're going to write an electron configuration for this, I see that as being like the front desk clerk's little notes, because you need to keep track of where the electrons are so that when somebody else comes in, you don't try to stick them in the same room, right? So this would be 1s has 2 electrons, 2s has 2 electrons. How many are in the 2p room? 6. And then next is 3s, there's 2 in there. And then 3p, there's 6 in there. And then how many in 4s? Just 1. This is a place where we do write the 1. So that's the electron configuration for potassium. Any questions? Does all that other stuff make a little more sense now? You have a question?
All those numbers will always add up to the number of electrons, right?
Yes. The superscripts here, 2 plus 2 plus 6 plus 2 plus 6 plus 1, adds up to 19. Always. Mm-hmm. Anybody else? Okay, so let's look at this slide again. The electrons occupy the orbitals to minimize the energy. They're going to fill the cheaper rooms first. That makes sense, right? Orbitals in the same sublevel have the same energy. Beds in the same room cost the same amount of money. Because how could you say, well, no, if you sleep in this bed, you have to pay more than if you sleep in that bed in the same hotel room? It's not going to work. Orbitals in the same sublevel have the same energy. The orbitals can hold no more than 2 electrons. The beds in that hotel can hold no more than 2 people. They can be empty. They could have 1 person, or they can have 2 people. 3 is not possible. And the Pauli Exclusion principle says, if you're sleeping together, you got to sleep opposite ways. Hund's rule says take your own bed first and sleep right side up in the bed. Okay? Yes?
So say you're doing carbon, would you still fill the one with the 3 rows? Would you still fill it one by one?
Well, let's do carbon. How many electrons in carbon? 6. So I'm going to go, oops, pick a pen, any pen. So 1, 2, 3, 4, 5, 6. So that'll be the electron configuration for carbon. I'm sorry, that would be the diagram. When we write that out, we're going to get 1s2, 2s2, 2p2, and we see 2 plus 2 plus 2 equals 6. Okay? Once you get your brain around this, it's nothing like trying to understand the orbitals. The wave function business, that's trippy stuff. This is just bookkeeping, basically. And so the electron configuration business is really, really important because it helps us to understand the periodic table and the behavior of the different elements. I'm getting lost. Okay, that's where I was. Here I am now. Okay, so unless we say otherwise, when we say electron configuration, we mean the ground state, the lowest energy configuration, all the electrons in the lowest possible energy orbitals. Okay? The number of electrons in a neutral atom always equals its atomic number. The atomic number is the number of protons. Now, you might wonder, well, if we have 2 electrons with negative charges, how can they be in the same orbital? I thought those repelled each other, right? Kind of like, assuming guys and girls are attracted to each other, then how would you have 2 guys sleeping in the same bed, right? Wouldn't they be repelled? Well, that's why they're sleeping upside down. And that's not what this next thing is about. They can coexist because of the opposite spins within an orbital. But within the sublevel, the parallel spins minimizes the repulsion. So that's not a big deal. I guess I don't actually understand that very well. Each orbital can hold a maximum of 2 electrons. We already covered that. Okay, so the electron configuration is just a listing of the sublevels in the order of filling. Okay? In order of filling. So you'll notice that 4s comes before 3d. If you switch those around, I'll mark it incorrect, and Mastering Chemistry will say it's wrong also. It has to be in the order of filling. So, and it's got the number of electrons in each sublevel written as a superscript. So you can imagine, here's krypton, that's a lot of letters and numbers. You think about writing electron configuration for like radon, 86 electrons, that's going to get super tedious, right? We do have some shorthands. So a shorthand way is often called a noble gas configuration. And what we do is we represent all of the inner electrons using a noble gas symbol. So here's rubidium, 37 electrons. And how many electrons does krypton have? 37. No, krypton has 38. Krypton has 36. What the heck? It's right there. What is wrong with me? Yeah, 37 minus 1 is 36. That's the electron configuration for krypton. It's written right up here. So instead of writing all of that junk, we write krypton in brackets. So krypton in brackets, this stands in for all of that, and then we just write anything that comes after that. You can only do it with the noble gases. Yes?
So if you wanted to get a noble gas, how would you do that?
Well, if you wanted to use a noble gas configuration for a noble gas, let's do krypton. So you could just say, well, that's krypton, but that kind of seems cheating, doesn't it? It's like, Well, if we're going to do it, then we're going to look for the previous noble gas. Well, what's the previous noble gas? It's argon. right? So is argon, and argon is going to be these electrons right here. Argon has 18, and so it's going to be these first 18. 2, 4, 10, 12, 18 electrons. And so then we would write what comes after it. 4s2, 3d10, 4p6. Okay, good question. Anybody else have a question? I think there's a 3A worksheet where they ask them to do the noble gas configuration for helium. Well, the only way you can do that is to put helium in brackets because there's no smaller noble gas to it's a stupid question. So here's some electron configurations. Lithium, beryllium, boron, carbon. Here's the number of electrons. Again, that's the same as the atomic number for the element. These are the electron configurations. These are orbital diagrams. You should be able to write both. The electron configuration is the 1s2, 2s2, 2p6 business. The orbital diagram is drawing a picture. So here's the 1s orbital, sticking 2 electrons in there. Here's the 2s orbital, stick an electron in here. So in the quantum hotel, there's 1 bed for that room, 1 bed for this room. The 2p room, though, has 3 beds, so it has 3 boxes. And you stick the arrows in. This takes up a lot less space and is easier to look at than the picture I was drawing earlier, right? This one over here. You kind of want to have that in your head that that's what it is, but electron orbital diagrams are going to look like this, okay? So write electron configurations for each element. Orbital diagram. You know what? I'm going to skip ahead and get to the periodic table part, and we're going to come back to this. We'll come right back to that.